Now we'll be talking about more properties of logarithms, and we'll also discuss something called the change of base formula. So first, let's talk about this change of base formula. Those are these two formulas you see up in the top box at the beginning of the notes. And this isn't a proof. I shouldn't use the word proof, but just to kind of prove to you that this guy works, that these two formulas work, I want to remind you that we already know from working with logs, we know that log base 2 of 8 equals 3, right? Meaning 2 raised to the third power equals 8. Remember, a log is an exponent, and 3 is the exponent that gets us from our base 2 to our result of 8. 2 to the third power equals 8. So we know this, right? Or hopefully we know it by now. All right, so let's take a look at this change of base formula. So the guy on the left says log base b of m is equal to log of m divided by log of b. So why on earth do we have this change of base formula? Remember that on our calculator, we have a log button, meaning log base 10, common log, and we also have our ln, our natural log button, base e. So if we're trying to evaluate a log of a different base that's not base 10 or base e, we can use either of these two formulas. We'll get to the natural log in a second, but we can use either of these two formulas to calculate this, to estimate this. So log base b of m, let's say we're trying to evaluate log base 2 of 8, which, spoiler alert, it's going to be 3, right? But let's pretend like we don't know that. So log base 2 of 8, what on earth could that be? We could figure this out in our calculator using this change of base formula. So log base 2 of 8, according to this formula, should be equal to common log of 8, the big guy, the argument, divided by common log of 2, the little guy, the base. So let's test this out in our calculator, and I'm using the common log button, base 10. Notice there's no base in that formula, or no base that's written. So I'm going to take my log button, log of 8, and notice that my cursor's in the parentheses, so I'm going to use that right arrow to just scoot out of the parentheses, divided by common log of 2. Enter, and there's our 3. Okay, so we already knew this, and of course log base 2 of 8 is really quick to just do in our head. I wouldn't recommend that you use this change of base formula for that, something that straightforward, but just kind of showing you that this works. Let's do it again over here on the right using natural logarithms. So again, log base 2 of 8, according to this formula with natural logs, should be equal to natural log of 8 divided by natural log of 2. So let's see if this works in our calculator. Natural log of 8, use the right arrow to get out of the parentheses, divided by natural log of 2. And there's our 3 again. Okay, so the advantage to this change of base formula is it uses the log button or the ln button, both of which appear in our calculator, because we don't have a log base 2 button, right? So where this really comes in handy is if you take a look at number 1a, it says evaluate using the change of base formula round to the nearest thousandth. So we have log base 7 of 3. So that's asking us 7 raised to what power equals 3? I don't know. It's certainly not like a 2 or a 5 or anything simple like that. So because I can't quickly and easily tell what the exponent is, like we did with log base 2 of 8, so because I can't figure out what this exponent is in my head, let's use the change of base formula. So we can just use the common log version for this one, doesn't matter. So log base 7 of 3 should be equal to common log of 3, the big guy, over common log of 7, the little guy. So let's type this into our calculator. Common log of 3, get out of the parentheses, divided by common log of 7 equals, and rounding to the nearest thousandth, the third decimal place, we get approximately 0.565. Okay. And just to show you what that means, if we want to check our result, and this will be off a little bit due to rounding, but if I take my base of 7 and I raise it to the power 0.565 and I hit equals or enter, it should be about 3. And it's 3 and change a little bit because I rounded there. All right, for part B, log base 4 of 0.65, that's saying 4 to what power equals 0.65? I don't know. Do you guys know? I don't really know. So I'm going to use this change of base formula. And I can use the common log or I can use the natural log formula. Either one works fine. I'll just use the common log one again. So log base 4 of 0.65 should be equal to log of 0.65 divided by log of 4. Log of 0.65 divided by log of 4. And that gives me approximately, if I'm rounding to the nearest thousandth, negative 0.311. Okay. And again, that tells me that 4 raised to that power. So 4 raised to the power, and I'm rounding here, so negative 0.311 should give us approximately 0.65, and it does. All right, so that's our change of base formula. All right, so most of the rest of this video is going to be talking about properties of logarithms, and these are our 3 biggies, the product rule, the quotient rule, and the power rule. And these are very much related to our exponent rules. These are our log properties, our logarithm properties. Remember that a log is an exponent. So the way that exponents behave is very similar to the way that our logs behave because a logarithm is an exponent. All right, so let me start with our exponent rules over here first, just to remind you, because you know that these guys work. All right, so the product rule for exponents, for example, we know that x squared times x to the 5th would equal x to the 7th power, right? So we're multiplying, we're taking the product of x squared times x to the 5th, and we add the exponents to get 2 plus 5 equals 7, x to the 7th power. So we know that this works with exponents. We also have an equivalent product rule with our logs. So the product rule says log base b of a product m times n, you can write the little product in there to remind you if you want, log base b of m times n is equal to log base b of m plus log base b of n. So just like we added the 2 plus 5, we can add these two logs together. We're adding our exponents on the right, we're adding our logs on the left because logs are exponents. All right, so in number 2, let's just skip down here and apply this. It says expand using the product rule. So we have log base 2 of 5 times 8. Using the product rule, I can expand this into log base 2 of 5 plus log base 2 of 8. And the only additional thing that we need to do is, notice that we've got log base 2 of 8. We just talked about that a bunch a second ago. We know that we can further evaluate this. We can further simplify this. Log base 2 of 8 equals 3. So I'm going to write my final answer as log base 2 of 5 plus 3. So that would be my final answer. All right, please, 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 listen up. If you spaced out, listen up right now. Please, please, please don't write that this is equal to log base 2 of 8. I know 5 plus 3 is 8. That's fantastic. Log base 2 of 5 plus 3 is not the same thing as log base 2 of 8. So please don't add the 5 and the 3 together. I know you want to. Don't do it. It's totally wrong. Just know that that's a common mistake that we see a lot, and just don't do it. And speaking of common mistakes, another common mistake that we see is people improperly using the product rule. So log base 2 of 5 times 8 is not the same thing as log base 2 of 5 plus 8. That's not a thing. So that's not how the product rule works. So remember, we're splitting this log. Think of like physically splitting a log with an axe. We're taking one log, splitting it into 2 pieces, okay? So the log of a product equals 2 logs added together. That's how the product rule works. Okay, so let's take a look at our next example. ln, natural log of 8x. I'll use a different color here. So we want to expand this using the product rule. So this would be equal to natural log of 8 plus natural log of x. And I can't evaluate that any further, so that would be my final answer. Part C, common log, log of x times y. If I'm expanding this, I can just expand this to log of x plus log of y. I split this into 2 logs, and I'm done. All right, so that brings us to our quotient rule. So up back in this box, let's remind ourselves of how it works with exponents, the quotient rule with exponents. So if I had x to the 5th power divided by x squared. Of course, we could simplify this to x cubed. We're taking the exponents, 5 minus 2, to get our new exponent of 3, right? So you guys know that this works with exponents. Remember that a log is an exponent. So quotient rule for logs, log base b of m divided by n. There's our quotient in there. We're going to split the log in two. So log base b of m divided by n equals log base b of m minus log base b of n. So just like with our exponents, we subtracted. With our logs, we're going to subtract as well. So jumping down here to number 3, expand using the quotient rule. Log base 2 of 5 divided by 8 is equal to log base 2 of 5 minus, because we're using the quotient rule, log base 2 of 8. And once again, we can go ahead and simplify or evaluate log base 2 of 8. We know that that's a 3. So we want to go one step further and write this as log base 2 of 5 minus 3. And I know you're tempted, but please don't write this as log base 2 of 2. Don't do it. It's totally wrong. Please don't do that. Log base 2 of 5 minus 3. Two separate terms. All right, let's continue with part B, natural log of 8 divided by x. So using our quotient rule, this is natural log of 8 minus natural log of x. And that's it. We can't evaluate that any further. And if we wanted to, we could type natural log of 8, of course, in our calculator, but it's not a cute number. It's certainly not an integer. So that's why we're not going forward to simplify it, where in example A, log base 2 of 8 turns into a nice, lovely 3. So we go ahead and evaluate and simplify there. All right, part C, common log of x divided by y equals log of x minus log of y. Okay, cool. And on to our third property, the power rule. Let's remind ourselves of how exponents work first. So if I have, for example, x cubed, and then I raise that to the second power, x cubed raised to the second power is going to equal x to the 6th power. So when I have a base raised to an exponent and then I raise that whole guy to a new exponent, I'm going to multiply my products together, right? Multiply my exponents together. So 3 times 2 gives me 6. So I multiplied my two exponents together. In the same way, if we have log base b of m, so I'm over here by the power rule on the left, log base b of m raised to the power p, I can multiply my two exponents together. The p is an exponent, and then remember my log is an exponent. So I'm multiplying these guys together. So the effect is when you have an exponent, you can carry it forward as a product, as a coefficient out in front of your log. So looking at number 4, it says expand using the power rule. Log base 2 of 8 raised to the 4th power. Applying that power rule, I can carry that 4 out in front and write 4 times log base 2 of 8. And we know from before, we've seen this a few times now, that log base 2 of 8 is equal to 3. I carried on the 4 from before, so 4 times 3. So that whole thing simplifies to 12. All right, part B, natural log of x cubed. I can expand that. Let me change colors here. I can expand that using the power rule by carrying that 3 forward. So 3 times the natural log of x. And if you want to leave that multiplication symbol in there, that's fine. You can also write it as 3 times the natural log of x. Just looks a little cleaner that way. Just like in our final answer, if we're writing like the answer is 3x, we wouldn't write 3 times x, we just write 3x. So it's the same kind of idea. So the 3 is multiplied by the natural log of x. So you can use the multiplication symbol or not. And finally, part C, log of cube root of x. So with logs are exponents, so it's helpful first to get this into an exponent notation. So I would start off by rewriting this as the log of our base x, And instead of cube root of x, that radical notation, I'm going to write it as its equivalent rational exponent, x to the power 1 over 3, x to the power 1/3. And using our power rule, I can take that power, move it forward. So this is equal to 1/3 times the common log of x, or we can just write 1/3 log of x. Either way is correct. We know that the 1/3 is multiplied by the log of x.